Okay, morning everybody. Thanks for coming. We'll make a start. Just to say, we'll be doing a group photo after the tea break today. We'll be outside the department. I think likely we'll go round. There's a kind of a nice bit with the plaque of the department, kind of the name on the thing, and stand for that. Some great photographs taken. So we'll do that after the tea break. But this morning, very delighted to say we've got Paul Agnew, who's been sitting amongst us doing tutorials this week to talk about air quality forecasting applications.
Thank you, Luke. Morning, everybody. So I'm Paul Agnew. I'm from the Met Office, where I work in the Atmospheric Dispersion and Air Quality Group. I'll be talking about applying UKCA to air quality forecasting. I haven't met anybody yet who is working on air quality, but increasing numbers of climate modelers are also starting to look at air quality. And you never know what direction your PhDs might go in, so some of this could well, if you think it might not be immediately relevant to you, it might be at some point in the future. So I'm going to just go over some of the basics of air quality, say a little bit about air quality observations in the UK. My talk will be really focused on the UK and Northwest Europe because that's the domain that our forecast model operates on, but it will be relevant to other parts of the globe as well. I'll describe our operational forecast system, how it's configured, including UKCA. I'd like to say a little bit about how to validate an air quality model to check that the model is giving sensible results. And then I'll say a little bit about we've all become familiar the last few days with the different chemistry mechanisms within UKCA. Not all chemical mechanisms are alike, and I'll say a little bit about the performance of the different mechanisms for air quality applications. And then finally, I'll come to some work that's in progress, where we're coupling a different model, not the UM, but the name dispersion model to UKCA. That works at a relatively early stage, but I'd like to just say something about it. And then finally, I'll just mention a couple of data sets which may be of interest to people at some point if you ever come to work on applications of air quality. So I want to just start with the headline, which is that UKCA has been used to deliver the UK National Air Quality Forecast since April 2014. So it's really, it's not just a research application. It's been used to deliver this operational forecast every day of the week for 8 years now. So if you've ever driven around parts of the UK, you may see one of these strange boxes on the roadside. This is an air quality monitor, a roadside air quality monitor. So when we talk about air quality, clearly lots of different pollutants can find their way into the atmosphere, but in terms of air quality, we're generally talking about a particular subset of the commonly emitted pollutants which arise in the course of normal human activities. So that includes NO2. I've put carbon monoxide in brackets for a reason I'll come back to. SO2, ozone, and then the two PMs, PM10, PM2.5. And of course, the importance of these pollutants is that elevated concentrations of them can affect human health. What's deemed an acceptable concentration varies from country to country, but governments, certainly in Europe and across the world really, are required to warn the population if elevated levels of pollutants are expected. The legislative background for the UK, despite Brexit, is still a directive of the European Commission on ambient air quality and clean air for Europe, which gives a very detailed specification of the regulations that governments have to adhere to, both in terms of controlling emissions, controlling air concentrations of pollutants, and what steps they must take to warn the population in the event of air quality episodes. And another relevant aspect of this is a report by the Committee on the Medical Effects of Air Pollutants, COMEAP. It's a UK government-sponsored committee which advised the government on the effects of health on the impacts of pollutants on human health. So since 2014, the Met Office has been responsible for delivering the national forecasts. In the UK, oddly enough, the Met Office itself isn't responsible for delivering an air quality forecast. It falls to the government department, DEFRA. And I'll come back to the DEFRA website in a moment. But the thing that we actually forecast is something called the Daily Air Quality Index, or the DAQI. Clearly, I've mentioned the 5 pollutants which contribute to routine air quality, and it would be ridiculous to expect the public to interpret, air concentrations of multiple pollutants and try to figure out what that meant for human health. So the idea of the DAQI is that it takes suitably time-averaged values of the air concentrations of all those pollutants and combines them to make a single index which goes from 1 to 10. It's very badly named, actually, the Daily Air Quality Index. It's actually an air pollution index. You'd think that for a daily air quality index, that 10 would be the best air quality. But of course, it's the other way around. It's 10 is the worst air quality. And that causes problems when you're trying to communicate to the public. You won't. I don't expect you to read this chart in detail, but you can see this on the Met Office website or the DEFRA website. But it's the recipe for how you actually compute the Daily Air Quality Index. So taking time averages of the different pollutants. So for ozone, it's a rolling 8-hour mean. For the 2 PMs, it's a daily average of the 24-hour hourly values. For NO2, it goes on an hourly mean. For SO2, it's actually based on a 15-minute mean. Carbon monoxide used to be a pollutant of concern in the UK, but since 2012, levels had fallen significantly, and it ceased to become a significant problem. So in 2012, the DAQI was redefined. CO was taken out of it, but PM 2.5 was added into it. There weren't, prior to about 2009, there had not been that many observations of PM 2.5 routinely in the UK, but that increased in 2009 with the addition of a lot more sites to the UK network. So the main place for seeing what the forecast is in the UK, again, oddly enough, is not the Met Office, but it's the DEFRA website. And if you just Google UK Air, this is what you'll find. But the Met Office is responsible for supplying the information that goes on to this. So we produce maps of the DAQI out to 4 days ahead. There's a text forecast which does a number of things. It helps, it interprets the maps. If for any reason the forecast is not performing particularly well, it's a chance for a human forecaster to intervene and to add some disclaimers or qualifiers or caveats. And it's also tweeted to anybody who wants to receive the tweet. We're very fortunate in the UK with a good network for routine measurements of the air quality pollutants. That's funded by DEFRA. It's referred to as the Automatic Urban and Rural Network, the AURN. You can see a map on the right-hand side there. Coverage pretty good over England, bit more sparse in Wales, especially Western Wales, coverage not particularly great over the Highlands of Scotland, but then much smaller populations up there and less pollution. There are different types of sites: roadside, urban background, and rural locations, because the characteristics, obviously, of the pollutants differ according to what and how much pollution is being produced in different places. And hourly mean values are available, and you can see these very, very easily on the DEFRA website. If you go and click on a particular site, you can get the current recorded value, and you can also get a nice time series graph of what's been happening for the last 7 days. Over London, there's an additional network called the London Air Quality Network, operated by Imperial College. And many of the local authorities over the UK also have roadside monitoring, which they're required to put in place at particular traffic hotspots where pollution values are higher. One thing just to be aware of is that not all sites measure all pollutants. So if you just glance at this map and take it at face value, there is a kind of a sampling bias built into it, because you'll sometimes take these 3 sites on the East Anglian coast here. You might see this is Norwich Lake and Fields. You might see that showing elevated values of ozone and a daily air quality index of being displayed of, I don't know, 5 or 6, but the sites right next to it, you're only showing 2, and you think, okay, what's going on there? Well, actually, those other sites may not even be measuring ozone. So just a slide to describe the characteristics of UK air quality. Compared to many other countries, pollution levels are relatively low in the UK, nothing like on the scale of pollution that you get, say, in parts of China and parts of India. And in terms of the DACI, most of the time in the UK, the daily air quality index falls in the band 1, 2, or 3, which is grouped together and just called low. There are times during the year when we have air quality episodes, typically 10 to 15 or so a year, when elevated levels of pollutant will come. Almost all of those episodes are driven by either or both of ozone and PM 2.5. Sometimes you might get a PM 10 episode, say if there's like Saharan dust or something, where you've got very coarse aerosol being transported to the UK. Most of the time, the anthropogenic aerosol over the UK is dominated by, it's in the PM 2.5 component, but for something like a Saharan dust episode, the coarse component could dominate. Ozone episodes typically appear May to September. Obviously, ozone's photochemically driven. The episodes in the UK will typically be somewhat less intense than Southern European countries, of course. In terms of PM episodes, PM 2.5 episodes typically occur in spring and autumn. They're usually driven by a low pressure, a high pressure synoptic system to the east or southeast of the UK, which is drawing air from the Low Countries. And all the pollutants produced there, and all the precursors, as they pass over the sea, they can form secondary inorganic aerosol, in particular, over the UK. And in those sorts of episodes, ammonium nitrate is a very important, usually the dominant pollutant. So we have a a forecast system at the Met Office. It comprises a number of components. There's the AQM model, that's air quality in the unified model. I'll be saying more about that, but that's a configuration of the UM which uses UKCA. The weather forecast systems at the office, I mean, globally, you'll know there's a very large, very sophisticated global system of meteorological observations, which are collected by Met offices across the globe, and including the UK Met Office, and those observations are used to feed into the model via the data assimilation framework to improve the initial conditions of the model. We don't use air quality observations they're not assimilated into the model, but we use them in two ways. We have a bias corrections post-processing system. So after the model has run and produced its output, we make a statistical adjustment to the model based on the most recent observations. And we also use the observations for verification. So working out how well the forecast has performed compared to what's actually observed. And then that all comes together to produce the DACI forecast. So AQM itself, it's a limited area configuration of the UM. We started developing it circa 2005. It became operational in 2010. It runs at a relatively coarse resolution for a limited area model these days. The UKV model, which provides the weather forecast for the UK, runs at 1.5 kilometre resolution. And we are running at roughly 11 kilometre resolution. So it's still a relatively coarse resolution. There are various problems. The way in which just increasing the model resolution brings an improvement in skill to weather forecasts seems not to translate so easily to air quality forecasts. So just increasing the resolution is not the panacea that it is for a weather forecast. It's a whole atmosphere model. It goes up to a, well, okay, not into the stratosphere, but it's got we don't do prognostic chemistry in the stratosphere. Model top is around 39 kilometres with 63 vertical levels. So many of you probably working with the global models and not so familiar with limited area models. So a complication for running a limited area model is that you need to prescribe conditions at the boundaries of your model domain, whether that's conditions of meteorological variables or of composition, chemistry and aerosol. So for our LBCs, our lateral boundary conditions for meteorological parameters, we take those from the Met Office global model. And for the composition, so the chemistry and the aerosols, we take that, oddly enough, not from a Met Office model, because the Met Office doesn't run a full global chemistry model in the forecast suite, but the European Centre does. ECMWF, formerly based in Reading, now moved to Bologna in Italy. But they run the CIFS, the chemistry IFS model, and that provides the LBCs for our chemistry. AQM, I said it runs UKCA, and it does for gas phase chemistry. So we don't use any of the mechanisms which we've been working with this week, the CRI-STRAT or the STRAT-TROP mechanisms. We developed, in the early days of AQM, we developed this regional air quality mechanism, the RAC mechanism. I'll come later to talk about some of the differences between the chemistry mechanisms. But it has 40 transported species, 16 emitted, 116 gas phase reactions, 23 photolysis reactions. We use the FastJX photolysis scheme. That when we initially started developing, we were using the offline 2D photolysis scheme, but going to FastJX brought us a substantial improvement in forecast skill. It has representative alkanes, alkenes, and arenes, and importantly, since 2015, 2016, it includes the heterogeneous hydrolysis of N2O5 on the surface of aerosol particles, which is a very important mechanism in nighttime chemistry for producing nitric acid, which can go on to react with ammonium to form ammonium nitrate, secondary aerosol. We are still using an older aerosol scheme called the classic aerosol scheme, which was the scheme developed for climate modelling prior to GLOMAP becoming available. It's a single moment scheme, so it just the traces are aerosol mass, and the aerosol types are sulfate, black carbon, organic carbon, biomass burning, dust, and nitrate aerosol. The emissions are absolutely key. So the AQM is predicting, we run with a 5-minute time step, and the model is producing hourly mean values of pollutant concentrations. So it's having a good representation of your emissions is absolutely key. We're very fortunate in the UK to have something called the National Atmospheric Emissions Inventory, again funded by DEFRA, which is a bottom-up inventory of all of the important anthropogenic pollutants in the UK, and that's freely available on the NAE website. Our domain goes outside of the UK. It covers much of northwestern Europe, so we need more than just UK emissions. So many of you might be familiar with the EMEP, European emissions. EMEP's a European organisation which also provides a European wide emissions data set, now at 10-kilometre resolution. And then these inventories are all annual total emitted values. So inevitably you have to provide your own estimates of temporal profiles, so how the emissions vary through the day. So, for example, for NOx emissions, obviously rush hour peak traffic times, emissions during those periods can be very different to the middle of the night. And also vertical profiles for certain sectors. The emissions are divided into a number of different sectors, depending on what the origin is, whether it's, for example, emissions from traffic or industry or domestic. And it's often relevant to consider the injection height of those pollutants into the atmosphere. So you have to add a lot of additional information to the bare inventories. Sorry, there's the European emissions, the EMEP, and you can see the shipping tracks. Shipping plays an important contribution to the European emissions. In terms of the way the model is run, so just as we've been doing this week, running a row suite, AQM runs in the Met Office operational suite under a cycling row suite. The forecast model is free running. There's no data assimilation, either of weather variables or of chemistry and aerosol variables. But I mentioned this post-processing bias correction, which uses the observations. The initial conditions I mentioned for for meteorology coming from the global model, for composition. So the initial conditions actually come from the previous day's T+24 forecast predictions. And then I've mentioned the LBCs, which we take again from the global Met Office global model for Met variables and from the CIFS for composition. We forecast out to 5 days ahead, so out to T plus 120 hours, and we relax to a set of climatological. Because the CIFS only goes out to 3 days ahead, we run out of, after 3 days, we run out of LBCs, and so we have a scheme for relaxing to climatological LBCs. So just to say that the Met Office invests a lot of effort and energy in verifying both its weather forecasts and in our case the air quality forecast to see how good it was, how good were our forecasts. We, in terms of model evaluation for meteorological models and for climate models, one often just uses metrics like a whole field bias or root mean square error correlation. For air quality metrics, it has for an air quality model, it has a fundamentally different character if it's being used to provide warnings. You have a particular interest in knowing if when the forecast for levels exceed certain thresholds which are linked to either to human health or to statutory reporting values. So for ozone, when the concentrations go above 100 micrograms per cubic meter, that's a significant threshold. And so we use a different verification methodology which employs a contingency table to say, did we forecast an exceedance of that threshold? Yes or no? In the observations, was that threshold exceeded? Yes or no? And there are various tests you can use to evaluate your skill in the prediction of the exceedance of those thresholds. If you're comparing different pollutants, say you want to know how your model, how good is my model performing the ozone prediction, the ozone predictions compared to, say, the SO2 predictions. Well, the ambient concentrations of those pollutants in UKCA are very different. Typically, ozone ambient values typically say 80 to 100 micrograms per cubic meter. For SO2, probably in the range from 1 to 10 micrograms per cubic meter. So if you want to compare skill for those very different magnitudes, you're forced into using normalized metrics, and there are various options for doing that. I won't go into too much detail now, but there are some specific metrics which are well adapted to for evaluating bias and error of the forecast in a symmetrical way, treating under predictions and over predictions in a consistent manner. And these metrics, which normalize with respect to the sum of the forecast value and the observed value, are particularly useful. I mentioned that for an air quality model, just increasing the model resolution is no guarantee of improved performance. And I just want to illustrate that with this comparison here of, let's just call them the red model and the blue model. And on the left-hand side, I'm looking at a plot of the model bias. So that's the averaged error. And you can see that generally the red model has a small positive bias, the blue model has a small negative bias. But when you come to the air quality episode, the red model over-responds to it and gives excessive predictions of this pollutant, in this case PM2.5. The blue model under-predicts. If you just look at the root mean square error of these two models, you can see that the red model has a much higher peak RMSE. The blue model has a substantially lower RMSE. So if you were just looking at the whole field error in the forecast, you'd look at this and you'd say, well, the blue model is performing better. So bias is the averaged error, root mean square error. This FAC2 metric is it's a measure of the fraction of the observations of the model predictions which are within a factor of 2 of the observed values. And again, you can see the blue model actually performs better there. But if we just go back, in terms of a warning system, the blue model would be completely hopeless, because when you need it, when you need advanced warning of elevated levels of PM2.5, the blue model completely fails to respond to those episode conditions. So actually the red model would be a far better tool for providing warnings. And this is just a particular time series at one site. This is for ozone measurements. Again, the blue model, the black dashed line is the observations. The red model doing much better in terms of the peak value there. I won't go into detail of this, but this is the contingency table that I was talking about, with where you essentially populate this table. If your event was forecast, your event being an exceedance of a threshold, was it forecast, yes or no? Was it observed, yes or no? You add up the number of times you met those conditions, populate that table, and based on that you can compute these conditional probabilities, so the hit rate and the false alarm rate. And you can see, if you do that, going back to the mean field metrics, the bias and the RMSE, this is where we said before, looking at these, the blue model looks like it's performing best. But in terms of these categorical metrics, the hit rate, you can see the red model. So a perfect forecast would be have a value of unity here for the hit rate. A completely rubbish forecast has a very small hit rate, and you can see the blue model has a very small hit rate there. So those are the sorts of metrics that you need to be considering if you're verifying an air quality forecast. And if you dig a little bit deeper into the two models here, you can see that this is the frequency distribution of ozone levels given by the two models. Drilling down into the PDF and what's happening at these higher values is a very important diagnostic for understanding how skillful your model is at predicting elevated pollution values. So just to say that summarising the standard metrics often used to gauge the skill of a weather forecast need to be supplemented by categorical metrics when you're validating an air quality forecast. There are some interesting ways to visualize performance of a model. In an earlier slide, I talked about these normalized metrics, a normalized mean and a fractional gross error. These, I don't know if people have come across these plots before. We call them soccer plots. You just plot the mean bias against the fractional gross error for each of your observations and observation sites. A perfect forecast is a point here at the origin. This is typically what you would get for ozone. You get a somewhat random set of distribution of points here. If you look at this for PM2.5, PM10 rather, you get this linear feature out this way, a kind of a linear feature out this way. And what this is telling you is that in this case, with the random distribution of points, your model errors are dominated by random errors, whereas in this case there's a systematic either negative bias in this case here, or positive bias in this case here. So those different ways of looking at the verification metrics can add value in helping you very quickly understand the character of the errors in your model. We maintain a near real-time verification system where we take all of the observations, we get a data feed of the AURN observations, and we're able to plot in almost real time series of observed values and compare our forecast predictions as well. That's an incredibly valuable tool for us in near real time monitoring the performance of the forecast model. And then it's often useful, the secondary pollutants in particular vary on a much bigger scale than some of the primary emitted pollutants, and it's important to understand what's happening across larger sections of the country rather than at specific sites. And so just looking at field plots is a very important thing as well, just to gauge the picture over the whole of the country. And if you these are the AURN sites where we colour them with respect to the observations, and so this is for the DACI. This middle one is for ozone. This one is for PM2.5. So, and this was our model forecast. So this was clearly an ozone episode because it's the ozone DACI which is colourful. The PM2.5 observations are all still in the low value. So we know that this episode's being driven by ozone. I mentioned our post-processing bias correction system. So there's a fundamental difference in the character of the meteorological atmosphere and the chemical atmosphere. For a weather forecast, it's very important to get the initial conditions of the forecast correct. And there's a whole methodology of data assimilation to try to get the best possible initial condition, because that influences the subsequent evolution of the forecast. For the atmospheric chemistry, that simply isn't true. The atmosphere loses its memory of the chemical state of the atmosphere on a much shorter time scale than it does for the meteorological variables. So for Met variables, that initial state can be remembered by the atmosphere for a number of days, actually. For the chemical state of the atmosphere, the memory of that initial condition, obviously it falls with time, but typically after 6 or 9 or 12 hours, the memory of that initial condition is lost. So that's why a traditional data assimilation approach to air quality parameters just doesn't work. It doesn't improve the quality of your forecast. Far more effective is to have a measure of the current biases in your forecast, whether your model is over-predicting or under-predicting, according to the most recent observations, and then nudge the model output in a way that replicates, in a sense, persists that bias. And so that's what we do. And for certain pollutants, it can be... For certain pollutants, it can be it can add a major amount of skill. So for PM10 in particular, where the emission inventories are very poor generally, this post-processing, so the raw model is the orange line, the post-process corrected is the green line, and you can see much closer to the actual measurements. So, chemistry for air quality. What are the requirements for a chemistry mechanism if you want to model air quality? Well, they're very different to those requirements for a climate model. For a future climate model, you need a mechanism which represents the longer-term average chemistry of the atmosphere. Short-term peak values are far less relevant. If you're, a climate model, you'll typically take all your hourly values if you have them. Your model time step may be more than an hour, but you'll end up averaging them to produce monthly or seasonal means. With air quality modelling, and especially in a forecast model, those short-term peaks are what you're trying to capture. And a chemistry mechanism which fits the bill for climate modelling can be very different to what fits the bill for air quality. So one thing we have done is quite recently, because we're stepping back to, with all the structural changes, both in UKCA, with it now coming out of the and being part of its own in its own repository, and also all the changes that you heard about yesterday from Ben about the next generation modelling system, ELFRIC. We wanted to step back and reevaluate what models we're using, what chemistry mechanisms, what aerosol mechanisms we're using. So we've undertaken recently a comparison of our RAC mechanism against other chemistry mechanisms. So in these plots, the blue curve is the strat-trop mechanism, which we've all been working with this week. The RAC mechanism is the red line, and the observations is the black line here. And so this is for, a run of the model for an ozone episode in May 2018, and you can see that the observed values have a long tail right out to say about 155 micrograms per cubic meter. Almost all chemistry mechanisms would struggle to really model this very high end of the PDF, but you can see that RAC gets much closer with up to about 135 compared to strat-trop, which struggles to get above about 110 micrograms per cubic meter. And if you look at the performance of the model versus observations on this quantile plot, you can see that very clearly here. In the mid ranges of ozone concentrations, both models do fairly well. The black line is the one-to-one model observations line, but but above about 100 micrograms per cubic meter, they start to diverge, and the strat-trop significantly underpredicts compared to RAC. RAC isn't perfect, not reaching the 1-to-1 line, but it's substantially better. That's just another example of it. So we wrote this report, and we concluded that overall the StratTrop scheme struggled under air quality episode conditions, often failing to show any indication of an episode, which the RAC scheme generally captured. You can see it in these two graphs here. These are the observations. Red is up in above DACI 7. You can see the RAC mechanism is picking up this episode here, but it's barely registering in the StratTrop mechanism. In an earlier slide, I said, so what explains this? In an earlier slide, I said that the RAC mechanism has representative alkanes, alkenes, and arenes. The StratTrop mechanism only has alkene chemistry in it. There are no only has alkane chemistry in it. No alkenes, no arenes. The alkanes are amongst the least reactive of the VOCs. This is a bar chart of the VOCs from the National Atmospheric Emissions Inventory, and you can see that if you look at the alkenes, so ethene here, propene, they're contributing significantly, and arenes up here, they're contributing significantly, and not including those in your chemistry mechanism is going to leave you with a mechanism which is less reactive and is not able to respond and produce high elevated values of those peak values of ozone. We also looked at the CRI. It's a much more complex mechanism than both RAC and StratTrop. It gave very similar performance for ozone modelling, as you'd hope. So CRI-STRAT would definitely be a candidate, of a viable mechanism to use in an air quality model. However, because of the many more species and reactions, it's about 3.5 times more expensive computationally. So going forwards, we haven't yet made a decision as to what mechanism to go with. It would be an option to go with CRI if we could live with the increased computational cost, but we haven't ruled out sticking with the RAC and doing the work that would be needed to put that into the ASAB framework. For aerosol modelling, I said we use the classic scheme. This is quite a busy slide, but it's just comparing the classic scheme with the GLOMAP scheme. So we've undertaken an evaluation recently. My colleague Florent Malavel has looked at whether GLOMAP is a viable aerosol mechanism for air quality modelling. Flo found that there were some interesting predictions where the two schemes gave very different predictions, and one of them was in both the dry and the wet deposition between the classic and GLOMAP. You can see so for classic on the left here, you can see the magnitudes of these deposition fluxes substantially different to what you see with GLOMAP. So that needs more work just to understand those and to have a clear picture of which one is in better agreement with observations. But and then another important thing, I mentioned the importance of secondary nitrate aerosol for those spring and autumn PM 2.5 episodes. The implementation in classic can sometimes just just way over respond and produce far too much ammonium nitrate aerosol. And there's an example here from 2020. It's reassuring that the GLOMAP implementation of secondary nitrate aerosols doesn't seem to be quite as overreactive as the classic scheme does. So I don't expect you to read this, but it's just to say that the overall findings of our evaluation of GLOMAP for air quality were pretty much that there are potentially meant, although there are still some things that we don't understand, like the behaviour of some of the deposition parameters. Certainly at this stage, it looks like GLOMAP is a viable candidate as a replacement for classic for air quality applications. Just to finish off, I'm going to say a little bit about a different model. You may have heard of the NAME model. It's a dispersion model. It's the model used by the Met Office in an operational sense to respond when there's a release into the atmosphere of pollutants due to an accident. So let's say a chemical tanker crashes on the motorway, or a scrapyard catches light and a pile of tyres goes up in flame and is spreading choking black smoke over the vicinity. The emergency services have a hotline to the Met Office, and the Met Office will produce a prediction very quickly of where the nasty stuff is going to be transported, and that's used by the emergency responders to advise their strategy for dealing with it. That was the origin of the name dispersion model. For many years, it was a Lagrangian dispersion model. So what that means, Ben talked a little bit about Lagrangian and Eulerian models yesterday. In an Eulerian model, you have a grid over your domain, and you define parameters at grid points. In a Lagrangian model, there is no grid. You're releasing notional Lagrangian particles to which you attach your pollutants. The Lagrangian particles are advected by the winds, which are read into the model, and move around in that way, and you track these Lagrangian particles. So it's an offline model. It's not producing its own meteorology. You have to have run an NWP model and stored all the wind data and other things in addition to wind, kind of on disk first, and then you read those into the model. So it has some other features as well, which are quite useful. It turns out it's possible to run a Lagrangian model backwards in time, so you can use that to see where air has come from at a particular time. So these plots here, this is the Chilbolton Observatory in Hampshire, and if we're measuring pollutants here, we can say over the last 48 hours where the air that we're analysing at noon on a particular day, where has it been over the last 48 hours? And you can see the back trajectories where the air's come from. That's often a very useful diagnostic for understanding where air has come from, what pollutants it might have picked up. So going forwards, with the transition to NGMS and the ELFRIC model, for a variety of reasons, we are starting to look more closely at stopping the development of AQM and developing NAME as an air quality forecast model. Recently, an Eulerian advection framework has been added to NAME. So it's still currently an offline model. It still needs to be fed with NWP from an additional model. But the idea is that we would use the UM or ELFRIC to generate NWP data, which is then read into NAME, which is then coupled to UKCA. Currently, NAME is not coupled to UKCA. It has its own chemistry and aerosol scheme, which has proven difficult to support. So the idea of coupling to NAME, coupling to UKCA and being part of the UKCA community is very attractive, and then using that to deliver an air quality forecast. So we have this project underway, New AQ, and the idea is that in a couple of years from now that we will have successfully coupled to UKCA, and that we've evaluated the performance of NAME for air quality modelling. That won't stop there though, because the whole concept of an offline model of needing this big archive of metadata that you have to lug around with you and read into the model. I mean, that's clearly very clunky. What you would really like is to have NAME embedded into your NWP model, which a few years from now will be the ELFRIC model. And so the thing that's missing is that big archive of NWP data. If NAME can be embedded into ELFRIC directly, then that will bring a host of benefits. You won't need this huge archive. You won't have the computational expense of reading in vast amounts of metadata. You'll have access to met parameters and chemistry and aerosol parameters at model time step resolution. So many benefits. But a lot of work needs to happen before we get to that. And then just very quickly, I just want to mention two data sets which, if anybody is interested in, and planning to work on air quality, particularly for epidemiologists trying to show relationships between air quality and human health, either through statistics of UK mortality or morbidity. So two very valuable data sets to be aware of. So we maintain a data set going back to 2012 of RT plus 24 forecast data, which gives, for the whole of the UK, a pretty high quality representation of pollutant air concentration values over that whole time period. Data sets available in the Met Office Mass Archive. We've also now recently put it onto Jasmine. And then another thing that we're doing as part of a big UKRI funded project is to generate a reanalysis of air quality. So that just, you may be familiar with meteorological reanalyses where people have, so you go back in time and you've got access to all the historic observations. You've got a consistent configuration of the model, and you rerun all of the data assimilation and the model runs, and you generate your best estimate of the state of the atmosphere and all the Met variables throughout the whole period. So we're doing something similar for air quality. We're going back to 2003, using all the observations that we can access, and running a configuration of AQM to get hourly values of pollutant levels all the way over the UK from 2003 to present day. We hope to have the first version of that by the end of March this next year. So we're really quite close to that. And then just very, very quickly, I just mentioned some activities. We are also, in terms of higher resolution modelling, there has been some work done as part of this UKRI project to couple AQUM to what's called a Gaussian plume model, something developed by a commercial consultancy here in Cambridge called the ADMS model, which is capable of giving predictions on a much finer scale. I have to say the jury's still out as to how much value that brings in terms of the improvements of skill for roadside predictions, but that remains to be seen. But it's a piece of work that we're involved with, and something completely different. The Met Office does make a pollen forecast, and at the moment it's done in a very almost unscientific way, in a sense. We're developing, using the name model, we're developing a model-based pollen forecast, which will replace the current forecast system, which just relies on expert judgment and kind of hand-wavy feelings about the way that the forecast should be for the next few days. So it will bring a model-based forecast with much higher resolution over the UK, and can be objectively verified against the admittedly very small number of pollen observation sites over the UK. So that's quite an exciting development. That doesn't use UKCA. It treats pollen just as inert traces. But who knows? In time, we may find it worthwhile to adopt UKCA for that work also. Thank you.
Thanks, Paul, for the retro. Are there any questions? Mark?
Going back to height, the model goes to 39 kilometres.
Yep.
Does that include things like aviation activity? And is that important?
We have aviation emissions in terms of the impact on UK surface air quality. It's pretty negligible. More important is actually having a good representation of all the cars driving to Heathrow. Yeah.
What about the emissions? So the emissions are very long and diurnal emissions in the model?
Yes, so we have a representation of the diurnal variations. So we have that on a sector by sector basis. Those variations, it can be difficult to validate them and to have them and to be confident that they're, because, for example, the people who operate steelworks and power plants, they're quite protective of their data, and they don't provide easy access to either the planned activities of their sites or even recent historically. So the diurnal cycles, yeah. You make a guess, you make your best estimate, and that's what you have to go with.
What's the typical computation time for your 5-day forecast?
The chemical
Computation time.
Oh, okay. So running AQUM for 1 day takes about 5 minutes. So for 5 days, 25 minutes. So it's pretty quick to run, actually.
Do you have to fit within that hour window that Ben was talking about?
Yeah. actually, the most computationally expensive part of our suite is producing the LBCs. We have to get the data from ECMWF's archives. We have to do various, cut out various domains. We have to do regridding. In some cases, we have to. The ECMWF model uses a different vertical coordinate system. It's a hybrid. It's a pressure-based coordinate system, and we have to, for parts of it, we have to put that onto the geopotential height coordinate system. It all takes time, and that's actually the most expensive part of our suite. But the whole suite, the model runs, round about midnight, and results are typically available to the forecasters by about 1:30 in the morning. Yeah. Yeah. So that was all chosen by this Committee on the Medical Effects of Air Pollution, COMIAP. They looked at all of the data which relates health impacts to observable, relating air concentration values to observable health impacts on people, and that was the basis for where to set the thresholds. Yeah. So the idea is that if you're put into a room with a high concentration of SO2, you'll probably start to be gasping after 15 minutes. For ozone, it probably take 8 hours. But yeah, those considerations.
Sorry, what you did mention, there's actually human interaction with this. People actually look at these before they write the forecast, I suppose. But is there anything like where you might spot an unexpected episode and you think, oh my goodness, something's happening? What's causing that?
Yeah.
Is that like one of the main activities?
Well, it can be. Things like Saharan dust coming into the domain. Obviously, we're reliant on that being present in the boundary conditions that we get from the global model. But let's say an Icelandic volcano explodes and there's a flow of volcanic ash, impinging on Scotland. That would be, we wouldn't have a representation of those emissions in AQUM. But that would be an example where the forecasters could say, northern Scotland. It looks like the maps are saying good air quality today, but remember that the volcano just erupted, and actually we're expecting a blanketing ash cloud to descend.
With switching from plastic to biomass, you just saying that biomass is that you just assume it must be better. Is there a reason why we think it might be best for us? Checking it out before.
You're right. You would think, it's a more sophisticated scheme, surely it's better. When you just look at it objectively, it becomes less clear. There's an additional computational expense, and other factors than the fact it has two moments instead of just one. Other factors, of which there are many parameters go into GLOMAP, I'm sure, and those other factors could probably more important. I haven't seen any evidence to date that having a 2-moment scheme is particularly valuable for air quality modelling. In the future, I don't know, it's possible, but...
Would you have to adapt your bias correction or post-processing to actually change the schemes that you use?
No, I don't think so, because that the bias correction is never interacting with the model and the model schemes. It's really just looking at the output PM10 or PM2.5. So how the model gets to that is irrelevant.